0.09 over 0.09 plus 0.27. Exactly the same thing. Right? Should be. Specificity should be 70%, right? Did you have a question on that, or? Okay. Does everyone see that? So always use the table, because the quicker you set the table, it's easier to, it's a lot more difficult, I think, to get information just from Baies theorem. You can just quickly get it out of the table and answer any question that could pop up on the comp exam using this table. If you know what I mean. So let me just tell you the rules of the comp exam. To pass out of this class, you need to get around 75% on the comp exam. And if you know this stuff, you'll get 15%. Okay. Nope. But I know it's on. Yep. It's used in all textbooks, though, the ABCD. So you'll see it in other textbooks. I'm using notation that they'll use in Rosner and everything like that. Actually, yeah, that's a good point. I forgot to mention the textbook. If you guys want to study out of a textbook, the Rosner 5th edition book, I think is very good, for a start. And don't go out and buy it if you don't have one. Whatever you need, we'll be having notes passed out in class, and I have review sheets that you can use. Oh, also, you know that the comp exam is open book, open notes? It is. So at the end, you will get a review packet made by me with all the equations. And you just look through that and find the equation you need. The hardest part about statistics is figuring out what test to use. The rest is just algebra. Like, all of this was a bunch of algebra. I'm sorry I had to put you through it, but you should see it at least once. But just figuring out what test to use and how to set things up and what the notation is, that's the challenge of statistics. Okay? That's why it's very important for you to do these problem sets, because you just have to do it to know it. Okay? This problem set is due tomorrow. I'll pass out the solutions tomorrow.
So we actually have to do the problem set?
Yes. You do. You hand in the problem set. Not that I could grade them, but I really want you to do the first problem set, so I want you to hand in the first problem set tomorrow, if possible. Okay. I really want you to do this problem set by tomorrow. Okay. Any questions on this? Because if not, then we will take a 10-minute break and then come back to the rest.
There's a mistake here. So in the Framingham Heights study, you don't have anything about prevalence.
Don't need it.
But you're asking for, in question A, probability of predicting disease for someone who doesn't have it is a positive test of not having disease, which is 1 minus the negative predictive value.
Yeah, we're going to use a different method to solve that. It's a different question. I'm asking about normal distributions. If you can assume that the underlying distribution is normal, you don't need the prevalence.
You don't need the prevalence?
Yep.
Okay.
We'll see. You'll see it.
Another question.
Yes.
I don't know, I did that, and it looked like they are not in fact independent.
I think you're right. Just by what we had gone over, the equations, showing independence.
I taught some of this stuff before.
Oh, okay. Yeah, sure. They're not independent.
While you were doing the early stuff, I was just here, but it looked like they're not independent. The way that you phrase it says that they are, so.
Oh, I forgot that. Sorry, yeah, that's just
the phrasing is really wrong.
No. They're supposed to be not independent. So yeah, you're right. I just wrote it wrong.
Okay.
I should have put show whether the events. I miswrote it. That's a good point. Thank you. Unfortunately, I don't think they do because it's not offered until January, so it wouldn't be there until January. Yep, they definitely do.
Thank you.
They do have them in the bookstore now? Okay, then I'm wrong. They must have them for the School of Public Health then. Hey, what's up? Nice to see you, man. Good to see you, dude. See you in the crowd. I'm sorry that you have to be forced to.
Sucks. Yeah.
You have to. You
I didn't take it first year or second year.
Okay.
So if I'm gonna be able to. You're doing a really good job though.
Oh, thank you.
For someone that's I've never noticed.
Oh, thanks. I hope so.
Yeah. No, I
Hope it's helpful. What's that? No, no.
So like, with your rule 1, I was trying to look at how your rule 1 like how you actually write out this stuff, and I don't see how like you could write this out as like probability of T plus and then D plus and then say T and D or whatever according to it.
Oh, so rule 1 would show that this is probability of T plus and D plus over the probability of D plus, right?
Right. But then just like does that help at all? Or, like
No, it doesn't help with this. But all it's showing you is that probability of T plus and D plus is just, whatever. It's not really a probability in this sense, I guess. No, it doesn't help.
So it doesn't help.
It doesn't help with this. Actually, it only hurts you in this.
Okay.
You never use rule 1 in this.
Okay.
I only use rule 1 to prove Bayes' theorem.
Okay.
That's all.
All right.
Makes sense?
Yeah.
No, that's a great question.
Yeah. What are you applying to?
Medicine.
Medicine.
For cardiology.
Oh yeah, right on. I'll stay here. I watched you on the waters, and I'm like, what's going on? You're doing your sub-I, and like, I see you again. I'm like, you couldn't be doing your sub-I again.
No, I'm doing radon. That's why I have time to do this.
Do they give you a TA for this? That's nice.
Yeah, it's pretty nice. Did you have a question? What's your name again? Oh yeah, Ram, you emailed me about this. What's your background? So you know all this. Why are you here?
The later statistics you do, I just haven't learned the statistics. I know I'll pick it up, but some things, I mean, I could read it myself, but I might as well hang out and see. I have a very small probability.
The rest will be kind of boring for you. Yes.
I'm still convinced that there's something wrong here.
Nope, because there's another way of saying this. You in normal distributions. But I'm going to get into...
Like if almost everybody got the disease.
So all I'm trying to say here, maybe I'm wording it wrong, but just say the cutoff is 260. Oh, well, I drew it on the wrong side. 260 here. Yeah. And these are your two populations. And these are the people with the disease, and those are the people without the disease. And these are normally distributed. Right?
Yeah.
So what is the probability of predicting the disease for a man who will never develop it? And this sort of extends that way. You're just looking for this probability under this curve. You know the mean, you know the standard deviation, and you know your cutoff.
Oh, so
Z equals x minus mu over sigma.
Then what I'm presuming, because what you have to do to get that is assume that you've got somebody who will never get the disease. Now you test what's the probability to test positive.
I mean, but we already have separated the populations into those who will never develop it and those
But
who will.
the way I read it is that you've got a test. You got somebody without the disease.
So if my girlfriend comes
That's
next
probably
year, that would be
that's
sweet.
possible.
Because then, yeah, you get a 1-bedroom and it's like $700 a head.
What's the probability of having 260 or above in a man who will never have the disease? So we're not even looking at the other distribution. We're just looking at one normal distribution and saying, what's the probability of it being 260 or above?
What's the problem set?
Yeah, there should be 3 sheets for the problem set.
It's like, 2 questions?
I don't know. It's maybe wording.
Okay.
Maybe it's just wording.
It's hard to word these things precisely.
I know. Yeah, that's the hard part. What's up? Oh, okay. Yeah, yeah, absolutely. You didn't find it back there?
Back at the hospital?
Yeah.
Someone must have picked it up. Or it's just...
Yeah, absolutely. No problem. Okay. And yeah, I don't see. I'm just gonna people just make sure you sign up with your name and email list if you haven't. I'll start in like 2 more minutes.
I have some questions on Amino later on. Is there a way that, like, say 5 minutes later or whatever, and ask you about it? Or...
Yeah, absolutely. I'm actually planning afterwards to take 5 minutes to explain the paper to people who are here. But what's your question on?
Yeah, it's on the paper.
It's on the paper? Yeah. So I was going to do that anyways.
Yeah, they cover it.
Yeah.
Okay,
Just remind me afterwards. Make sure before everyone leaves that I tell them. I'll tell them right now too.
Okay.
All right. Why don't we get started?
I
Ron.
have a
Ron's.
question. I left my notebook, which has my topology notes in it, at the blood drawing session point. If anyone picks it up, but I guess not since no one's jumping on this. Yeah, it's a 5-star notebook. Yeah, you found it. Oh, they did? It was both. Okay, thank you. Oh, sorry?
Okay, so we'll get started, but before you guys leave, just make sure you put your name and email address on the sign-up sheet. I'll just pass it around just in case people didn't sign up yet. And secondly, for those of you who are taking immunology, I'm going to spend I'll quit the class and then we'll spend 5 minutes afterwards going over the paper, just to make sure you guys know it for the quiz on Tuesday. All right? Well, yeah, they have quizzes. Yeah, the one on total-like receptors. So we can talk about that for 5 minutes if you guys have questions. And I guess that's it. Whatever was covered in lecture or in the camel. That's all that's covered. So that includes the paper. Okay? All right, let's get started. So when we're thinking about statistics, we usually think about collecting data or samples of data. And when we think of collecting samples of data, we want to be able to describe those samples of data. And so one way to do that, if you guys can see, just briefly, there are different ways of, not plugged in. There are different ways of describing data using graphs. See if you guys can see it. And so you guys should become familiar with the different ways of doing that. The first method is a stem and leaf plot. And this is short of giving you a sense of the distribution of data values. The first one being 105, and then 107, and then the second being 125. There are 225s and then 120. So this is what a stem and leaf plot would look like, and it sort of gives you a rough estimate of sort of where the values lie and how many there are. Okay? Okay, so good. I'm glad I did this because I wasn't sure whether you guys would think this would be useful or not. So a stem and leaf plot is one way of showing data. So just say you're looking at blood pressures, right? Or whatever. No, these can't be blood pressures, but maybe cholesterol levels or something. And the first number, 10, is the first two digits in the number, and 5 is the third digit. So one person had a cholesterol level of 105. A second person had a cholesterol level of 107. A third person had a cholesterol level of 125. Two of them actually had 125, and one of them with 120. A third one with a value of 145. See the wheels churning. It's excellent. You guys are learning. This is great. So, 165, 4 160s. So this is a way of sort of, in a graphical sense, showing the shape of the curve, but also giving you the exact values in a very concise format. Yeah. There are no odds. Well, whatever. I don't know why. This just happened.
Arbitrary within each column. You have to jump up a decade after. When you see a zero, that means the second zero. Like under where it's 20 on the left, it's 200 to a 5, and then 2 to 10. That last one is 2 to 10. Yeah. Which side of the number comes from? Because they're ordered. Oh, they're ordered. Well, what if they just touch 2 zeros? How do you represent like 2?
Wait, what are you saying? Wait, what are you saying about this plot?
Pick a line with
All right, this one. 165.
165, 170, 170, 170, 175.
Right. Yeah, it's going in between, and it's going in order of ascension. I didn't really want to discuss that. It's just, so you're choosing your bin sizes. Your bin sizes are 20. So every time you go down, you're going down by a bin size of 20. This is going to be 105, 107. No, you don't. I'm just trying to show you how how to illustrate data, right? We're only going to be focusing on the last one. This is a box plot which shows the mean, and you can choose what these points represent. These points usually represent the 25th and 75th percentile. Okay. And then these two ends usually represent the 2 standard deviations. Or whatever you want, actually. You can choose. I've seen a lot of variation. And then histograms. Now you can see here that these are 2 histograms, and what you're plotting here on the x-axis is whatever variable you're looking at. So this happens to be birth weight in grams. Okay? And on the vertical axis is just the number of babies with that particular birth weight. You can see here that depending on the bin size, your distribution could look very different. So, researchers use this technique all the time to make their distributions look nice. All the time. I used to do some physics research, and you could always, one bin size would make it look normal, another way would look at, trimodal. So it really depends on your bin size. So be careful of that when you're looking at data in papers. But that's not really crucial for the anything here. How do you put this down? Oh, this one? Thank you. All right. So that's how we look at data. And when we're describing data, we can describe the variables as either continuous or discrete, right? So continuous variables would be something like blood pressure, weights, anything that could have any value. And discrete variables, something like the number of cancer recurrences that a patient has. And that would have to be whole numbers. Other ways of describing samples are using mean, right? So the mean of a sample is defined as the sum of all the values from 1 to n divided by the total number, n. Okay? You guys, I'm sure, have seen this before. The variance of a sample, right? We sometimes denote it as capital S, also called S squared, where little s is the standard deviation. That's simply the sum of the squares of the differences from I equals 1 to n of xi minus x average squared. And instead of dividing by n, we divide by n minus 1. Tends to give better statistics, and that's what's used today, although physicists all the time will just divide this by n, so you can use either way. Yes. Well, for this class, you should use n over n minus 1.
What's variance like kind of conceptually?
So let's talk about that. It's essentially described as the spread of the data. I mean, you could have two data sets, one being 4, 5, and 7. Sorry, 4, 5, and 6, and the other being 0, 5, and 10. They both have the same average, right? 5. But this is much closer together than this, right? So it allows you to sort of describe the spread of the data, how spread out it is. And that's why you have to take the square of the differences. Because if you only took the value of it, it would be 0, right? If you just summed up xi minus x average, that by definition would be 0, because that's how you define the average. So that's why you have to take the square of it to make all the differences positive and then add those up. And so that's how you describe the spread of the data. So that's another thing. You can also describe it using the median, the middle number. Okay. Or what's the mode? The most frequent data point. Okay. So different ways of doing it. Well, this is one way to look at the variance. And another way is just, why don't we factor this out? So if you guys remember factoring out, this data, it's going to be xi squared, right? And when you factor this, it's, if you guys remember, it's going to be minus xi times x average, but because there are two of them, it's going to be two of those. So minus 2xi times x average. And then you multiply this with itself, so it's minus x average squared. Okay? So I just essentially factored whatever was in the parentheses. And the nice thing is this can simplify into the following. You get 1 minus n minus 1 times the sum of xi squared, right? Minus, now if we use our first definition here and plug in for this sum, xi, right? Well, let me just factor everything out. So let me do this. It's the sum of xi squared minus 2x average times the sum of xi plus x average squared times the sum of just 1. Remember, I'm allowed to factor out the x averages from the summation signs because those are just constants. The x average is just the average. It's a constant. Okay? And so when this simplifies, what you get is 1 over n minus 1 times the sum of xi squared. What is the sum of xi? Well, it's just n times x average. So I'm going to put that in. So it's 2n x average, and we have another x average here, so that's going to be squared. Plus, what's the sum of 1 n times? Because you're adding up 1 from I equals 1 to n. It's just going to be n, right? So it's going to be n x average squared. And what this then reduces to is 1 over n minus 1 times the sum of xi squared minus 2n x average squared plus n, so it's going to be in total minus n x average squared. And so when you see the standard, the variance written in this form, now you know where that comes from. Essentially, you're just factoring everything out. In general, with large data sets, it's much more convenient to use this definition of variance. Because in your calculator, you can put a list of data and say, okay, calculate the sum of x squared, or calculate x average, and then just plug in. Okay? All right, so that was just algebra. I didn't want you to get confused by that. There's just two ways of showing what the variance is of a group of data. Okay? Now what I really want to move into is normal distribution and binomial distributions. So, any questions before I move on, or? Open book, open notes, calculator, everything. Yep. No laptop. And you can't use your friends. Okay. So let's just look at distributions of data. No phone of friends. So we'll first talk about the normal distribution. And essentially that's just the bell curve. Right? And whenever we're describing a normal distribution, usually the notation is written like this, where you have the average and the standard deviation. So if I were to write n0, 1, that would represent a normal distribution with average of 0 and standard deviation of 1. Or variance of 1, but standard deviation of 1 as well. Okay? And sort of, do you guys remember what this function is for a normal distribution? Not that you should know it for the exam, but it'll help us when we're looking at binomial distribution. Well, it's not an integral. E to the minus x minus mu squared over 2 sigma squared. So you can see that when so if you were to plot this in your calculator, this equation, if you were to write that out, you would actually get a normal distribution. And you can see that this normal distribution depends on these two variables, mu and sigma. So that's what defines a normal distribution. It's mean and its standard deviation or variance, whatever you want to call it. Okay? All right.
U is the average, and then sigma is?
Sigma is the standard deviation. Sigma squared is the variance.
I think there's something like constant.
What was that?
I think there's a normalizing.
Yeah, I'm not worried about the normalizing constant. But yeah, you'd have to normalize it in order to make sure that the area under the graph was 1. Okay. Well, that's one distribution. We'll get back to this. This is very important. Actually, let me just say one thing also. Statistically, if we wanted to look at something out here, just call it x. Okay. The way we describe it is based on the number of standard deviations it is away from the mean. And usually I've seen that in textbooks called z. So it's the number of standard deviations, or the number of sigmas away from the mean. So all that is equal to the value x minus the mean divided by the standard deviation. So that's what we call z. It's the number of standard deviations you are away from the mean. So if you have a population of people with an exam with an average of 50% on the exam, and you're at 70%, which is passing for a competency exam, and not that the average in this class will be 50, the average will be 90, right? And the standard deviation is 10, right? How many standard deviations away are you? You can do it in your mind. You would do it all the time. It's just 2, right? So z is 2. Okay. Now, I want to talk about a little bit about the theory of binomial distributions, and then we'll leave binomial distributions and talk about them again tomorrow. And we'll return to the normal distribution a little bit later on today. But just to get into the theory of a binomial distribution. So, essentially, let's take the example of flipping a coin. With the probability of a head, it's a fair coin, so we'll say it's 1/2. Yeah?
So the definition of normal distribution is just one that fits that function?
Yeah, something that fits a function with a mean and a standard deviation. And in statistics, we'll assume that most things are normal. Okay? For the purposes of this competency exam, you can assume everything is normal unless they say that it's not, which we'll get into those examples next week. Okay? All right. So flipping a coin. So the nice thing about binomial distributions is that they're approximately normal in a lot of cases. And so we'll see how we can approximate them to a normal distribution. Remember, if it's normal, that means that it can be described with a mean and a standard deviation. But let's talk about the binomial distribution a little bit. So we're flipping a coin. Just say we flip it 4 times. And the question is, what's the probability of getting 1 head? That's our question. So how do we find that out? What's the probability of getting 1 head out of 4 flips? Absolutely. So the way he described it is perfect. So he's setting up the 4 possible scenarios that could get you 1 head. Right? It's any one of these. So there are 4 different combinations of flips that could get you 1 head. But then you have to divide that by the total number of flips that are available. And the way to do this is, the equation to remember is the following. So the probability of, just say, 1 head, or let me speak more generally. The probability in general of a binomial distribution takes this form. It's n factorial over, what should I call it? I'll call it x. X factorial n minus x factorial p to the x times 1 minus p to the n minus x. Now, this is something you do need to know. Again, this is an open book exam, so you don't have to memorize it, but you'll need to know how to use this equation. Okay? All we're saying here, so, and this is x, the probability of x is the probability of having 1 head in this example. So x is what you're looking at. X is the number of events that you're looking at, that you're interested in. P is the probability of that event. In this case, it's flipping a head, which is 1/2. Okay. And what do you suppose this term is for?
Sorry, so n is 4 here?
Yeah, sorry. N is the number of the total number of events. So I can be more specific and say x is the number of positive events, or whatever you want to call it. And n is the total number of events, and that's 4. In this case, we're only interested in 1 head, so that's what x is equal to. And so what is this little term for? Yeah, Salil?
So, quick question.
Yeah.
So, this equation works also if the probability is not 1/2.
It works for any probability, even if it's not 1/2. Absolutely.
So if you're talking about one that has how many times you can have one.
Absolutely. So it doesn't have to be 1/2. Yeah, if you want 2 heads out of the 4, then you would put n equals 4, x equals 2. Yes.
That factor is to make sure that you're not counting Because if you were setting it up with 2, if you didn't count head, tail, tail, head, and head, tail, tail, head twice, because you say I get a head the first time, and then tail, tail, head, and then head, tail, head, and then tail, head, tail, and then you're doing that again with the fourth time. You can only have one.
Well, essentially, it's just to get the number of combinations here, right? So we already knew that there were 4 combinations. Let's just plug in the number, 4 factorial divided by x, which is 1 factorial, and then 3 factorial. Well, 4 factorial divided by 3 factorial is just 4, and 1 factorial is 1. So that's your number of combinations, 4. The 4 that we had listed out here, right? So this term gives you the number of possible combinations that will give you this result, right? We can have one, which is exactly what you were saying. You can have one head, but 4 different ways of having one head, right? So this is the combinations term. Okay. And so the probability of having one head, if we were to calculate this out, is 4 times 1/2 to the first power times 1/2 to the third power. This term gives you the total number of possibilities of permutations, this factor right here. And that's going to be 4 over 2 to the 4th power, which is 16. So that's going to be 1/4, right? Okay. Let's now do that with probability of calculating 2 heads, getting 2 heads, okay, out of the 4. And again, I mean, if you went through every combination, you could do the same thing over and over, and you could figure out how many different ones there were. But that's the nice thing about this, is you can just calculate the term out in front, n factorial divided by x factorial. So remember, x is 2. You want 2 heads. We have a total of 4 flips, that's n, and the probability of a head is 1/2. Okay? So here are 3 terms that define a binomial expression, a binomial probability. Okay? And what you get here is the following: 1/2 squared times another half squared. Right? Does everyone see that? Because this is the probability of getting a head, and you get it twice, so you square it. This is the probability of not getting a head, and you square it, because that will have to happen twice. And this term is the number of combinations. So 4 factorial is 24. You guys know what factorial is? 4 factorial is just 4 times 3 times 2 times 1, everything down to 1. 2 factorial is just 2. 2 factorial is just 2. This is 1/2 to the 4th power, so that's 1/16. What you end up with is 24 over 4 is 6/16. Okay? What you're hopefully beginning to realize is that because our p-value is 1/2, these sets of terms, no matter what you choose, will always be 1/16, right? And it only depends on this term to get the actual probability. And if you were to calculate it out, all the different probabilities of getting 0 head, you would find that that's 1/16. 1 head would be 4/16. 2 heads, as we calculated, is 6/16. 3 heads is just the same thing as 1 head, right? Because getting 3 heads is equivalent to getting 1 tail. Why should a tail be different than a head, right? So that should be 4/16. And then how about getting 0 heads? Or no, sorry, 4 heads. What would be that probability? 1/16. Do these numbers, 1, 4, 6, 4, 1, remind you of anything? Pascal's triangle, absolutely. So when you have Pascal's triangle, if I were to draw it out, you have 1 and 1, 1, 2, 1. So remember, the trick is to just add them together. 1, 3, 3, 1, right? And then add these up. 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. You can use Pascal's triangle for the binomial expansion, and you know what those coefficients are. Okay? And so, if I were to ask you, what is the probability when you're flipping a coin 5 times to get heads 2 times or less, what would that probability be? So let's do that example. So out of 5 flips, what's the probability of getting 2 heads or less? That's our example. How would you do it? Which row on the Pascal's triangle would you look at? Well, you would look at the one that's the 5th row here, starting with 5. Okay, right? So this is for 0 flips, 0 heads, 1 head, and 2 heads, right? So when you add those up, what do you get? 16. Okay, and what's the total number here? 32. So it's 1/2. Does that make sense? We should make sense intuitively because you have a choice of either 0 flips, 1 flips, or 2 flips of heads, or 3, 4, and 5. So dividing in half should just be a probability of half.
This should be useful when the probability isn't a half.
You can absolutely use it when the probability is not a half, but in that situation, you can't just add them up linearly because this is just the coefficient. This term will then change if the probability is not a half. So then you'll actually have to do the calculation for each term out and then add them up, okay? So if the probability of flipping a head was not a half, you couldn't do the same calculation, 16 over 32. You would have to do each term individually with this term added, right? Because it's changing. It's not always going to be 1 over 32. It's going to be different depending on what your values are. Does that make sense? You guys okay? There's going to be practice of this, but essentially what I want to tell you is how to do this. So let me get this chart up. Yeah.
Do you mind going over why you, like for 2 heads or less, why you, because it's 0, 1, and 2, and so you added those up?
Right, I just added these up. 1 plus 5 plus 10.
Because those are the probabilities of 0, 1, 2.
Right. And then divided by the total. But you can only do that when the probability is 1/2 that you're looking at. If it's not, then it's no big deal. All you have to do is, you know the coefficients now, 1, 5, and 10. 1 times this, where x is 0, right? And then 5 times this, where x is, 1 for 1 head. And then 10 times this term, where x is 2. And whatever your probability is. Let's do an example. I'll do an example. And we won't even do the algebra, we'll just set it up. So just say you're in a world where the probability of getting a flu infection follows a binomial distribution and it's equal to 1/4. Okay? And you have a classroom of 5 students. Right? And you want to know what's the probability of 3 students contracting the flu. So this is our example. It follows a binomial distribution. And the probability of having a flu infection for the nationwide is 1/4, let's say. And you have a class of 5 students. And you want to know what's the probability of any 3 students contracting the flu. Well, it's just going to follow the same equation, n factorial over x factorial n minus x factorial times p to the x times 1 minus p to the n minus x. Where x, remember, is your 3 students contracting the flu. N is 5. That's your total number of students. And 1/4 is your P. Okay. So all you do is plug it in. N factorial is 5 factorial. X is just 3, so divided by 3 factorial and 2 factorial. So that's your number of combinations term. That tells you how many different combinations of 3 students you can get out of the 5. And then this is your probability term. That's just 1/4 to the 3rd power times your probability of not getting the flu, which is 3/4 to the 2nd power, because 2 students must not have the flu. So you have to do 3/4 squared. 3 students must have the flu, so it's 1/4 cubed. That's your answer.
You said binomial distribution, but if you are assuming that having flu and not having flu is binary, period, we would not consider this binomial distribution to do this?
With this what?
Is that redundant information-based binomial distribution if you tell us this is a probability of having flu in population?
Oh, I see. You're just asking, is it redundant? Did I have to tell you that it was binomial? Yeah. No, because I'm giving you a set probability of yes or no. Yes, they have the flu, it's 1/4. No, it's 3/4. So you can always use the binomial. I wouldn't have to say that. Yep.
So then when we call it binomial, we use outcomes.
Yeah. Yeah, for this equation, yeah, you're looking at binomials with either 2 outcomes with a probability of P and of not happening 1 minus P. Yes.
A couple things in practice. I wouldn't ask this question like that with the probability of 3 or more students or something like that.
Sure.
Second, properly having fluid doesn't follow the binomial distribution. People catch fluid from each other.
I agree. So that's a limitation of the study. But binomial distributions are often used in cases where they shouldn't in statistics. I agree. All right. I think this is just more for teaching purposes than actual real live examples.
If you would add
So, but when people, when people screw up, there's more ways they screw up.
Right. I mean, flus are obviously contagious, so, I mean, the fact that that would be, if you were asking the question 3 or more, would that be, and did this calculation and saw, wow, that's unusual for, given what the nationwide fraction would be, then yeah, you would argue, well, that's because flus are contagious, each event is not independent.
If you had asked 3 or more, would you do this for 3 and 4 and 5 multiply?
Not multiply, add them together. Add the probabilities together. So you would do the one for 4 and then the one for 5 and just add them up. Absolutely.
There's an equation for, there's a way to modify the case to do it more.
I think for the purposes of this class, we're just going to stick with just doing them in individual terms and then just adding them together. If there is a way of modifying it, I haven't seen it. So does this make sense? So just being able to use this equation to calculate a probability. Right? That's what you need to be able to do for the exam. Okay. All right. Well, let's move on then. And let's now go back to talking about normal distributions. And let's do it in the context of an example. Okay. So if we have a normal distribution, and let's just take exam scores, right? Because we're all used to that. And your average exam score was 70. You had a standard deviation of 10. Okay? So the question I have is, there are 2 parts. One question is, what is the probability that a student scores or scored higher than 85%. So how do we do that? How do we figure out that probability? Scott?
If you determine the z-score for that calculation, and then there are, you could either calculate it by doing on the map and then be able to revert it.
Absolutely. Right. So you calculate the z-score, which, just to remind you, is the number of standard deviations that you are away from the mean. Right? And so we're looking at 80, so the equation looks like x minus mu over sigma. And so our x is just 85. That's our test score. Our mean is 70, and our standard deviation is 10. So when you do out the algebra, that's 1.5 standard deviations above the mean. Well, because we know what normal distributions look like and what their equation is, tables have been come up with, tables have been formulated that allow us to figure out what our answer is. And for the exam, you'll have copies of these tables, but I think I'll try to get copies for you if you guys don't have textbooks. Does everyone have a textbook here with these normal tables, or would you guys need it? Probably. Okay, so I'll try to email you copies tonight. Okay. And so, let me just put this down. The way you read these tables, that's an art in and of itself. You have to know how to read them. And they're not too difficult. But I chose this one. It's in the back of Rosner because they give you 4 different areas. And unfortunately, the color didn't come out here, but in the first column, shade this area in. It's the big one. And then on this column, shade this area in. Oh, you don't have the handout, sorry. I'll email you the handouts. And C is this, and D is this. Sorry. And so, when you look at it, this X is your z-score. All right. So let's look at a z-score of 1.5, which goes on to the next page, right here. So here. This is your z-score of 1.5. It says that the area in column A is 93.3%. So look back at the area in column A. That's this area here, 93.3%. And this is your 6.7%, right? Which is what's shown in column B. So that's how you answer your question. If we're looking at what's the probability of having a student with this score of 85 or above, it's your 6.7%. Yes?
Is this percentile?
These are all areas, right? So let's just look at this. If you are, unfortunately this table doesn't go far enough, but just say you're half a standard deviation above the mean, right? So you're at 0.5. What that means is that you beat 69.15% of the people on the exam, right? And if that's where you're at, that 30.85% of the people beat you on the exam. So it is like a percentile, yeah. Absolutely. As long as everyone follows the normal distribution. Okay. Does that make sense? So a z of 1.5 corresponds to this point here, where 6.7% of the area is to the right of the curve, and 93.3% is to the left. That's how you read the table. You can also go backwards in a lot of questions, right? So if you want to say, okay, what percentile, like what score would I have to get to be at the 96th percentile? How would you do that? Well, if you wanted to be at the 96th percentile, then this area here has to be 0.95. Look for that area on the first column. It's not on the second page, because it's going to be on the third okay, if I want to be at the 95th percentile, I need a z-score of 1.65. And we know what the z-score is. It's x minus the average, which in this case is 70, over the standard deviation of 10. And so when you do the math, that's 16.5 equals x minus 70. So then x is going to be 86.5. That's the score you're going to need. That one's on, but this one isn't. This is for the taping. Alright, I'll try to talk into this. Hopefully that'll work. Okay. So does that make sense? What? I mean, does this seem pretty basic to you guys? Okay. Alright. So you guys need to get comfortable reading normal tables. Let's do another question now. Fortunately, with statistics, you have to go back and forth looking at these tables and then solving your question. The next question I have is, what is the probability that 4 students score greater than an average of 85%? What is that probability? 4 students. Well, I mean, just doesn't matter. Just assume this is the entire population. We don't need to know the total. Assuming no cheating. So what's the probability that 4 students score above it? How would that change things? Do you think that would make it harder to get 4 students? Hi. So I don't know why this isn't working. Are you Yetza?
I am.
Great, nice to meet you. Thank you for doing this. Is it working out okay?
Yeah.
Okay.
Anyway.
Okay. So just, how would that change things if you think about it? If we're now asking if 4 students can get an average, and you're choosing 4 random students in the population, not the 4 brightest or the 4 worst students, just you're choosing 4 random students in the population and asking, it's raising what? Well, not really. Wait, remember what I'm asking. Oh, I see what you're saying. Is it going to raise it to the 4th power? They're independent events. You could, definitely. If you need. Right. And the first probability that we calculated above, the 6 point, so looking at the table, what was it, 6.7%? Yeah, assuming if that was your binomial probability, then you could treat it like a binomial and then say that. I'm getting more at a more statistical approach using the normal distribution. How would you do it?
So you need, if you take 4 students out of the class, to calculate all of them with 85%, or do you need?
No, that their average is 45%. So, yeah, I think I said it, but I didn't write it. That 4 students' average score is greater than 85%.
So not just any 4.